So I'd made a bit of a claim earlier with vertical circular motion that the centripetal force is going to change depending on the position in the vertical circle, which will have consequences for other forces. I'd like to look at an example involving that very statement. So we've got two students. They're practicing yo-yo tricks for some yo-yo club, and one of the students are spinning a yo-yo with a mass of 0.82 kilograms around a vertical circular path with a radius of 0.50 meters and a speed of 7.9 meters per second. So what we're being asked to do is we're being asked to find the tensions at points A, B, and C. So you'll see A is at the very top, C is at the bottom, B is on the sides here. So each of these is going to have a slightly different tension. We expect that at the top is going to be the minimum, and then at the bottom we're going to have a maximum. But let's have a look. At the top of the vertical circle, so again, here's my center. We still have a force of gravity going down. And if the string is at this point, the tension, so the string being, if we're at A, the string is going to be along here. We're also going to have a force of tension. We're going to have a force of tension pulling towards the center of that circle. So keep in mind, for objects on a string, tension's always towards the center of the circle. And that's even worth writing. Ft always towards center. It wouldn't really make sense otherwise. So at point A, we know that the centripetal force is just going to be the force of gravity plus the force of tension. So we know towards the center of the circle, and I'm going to write towards center. Towards center is what we're going to call positive, which means away from the center by default will be negative. So the force of tension is going to be that centripetal force minus that force due to gravity. Or again, we have mv squared over r minus mg. So as always, the centripetal force will always be by default towards the center, so we will continue to call that positive. G is directed down, and it's towards the center of that circle, so we don't have to worry about negatives here. So we have that mass of 0.82 kilos, and then v squared, we said v was 7.9 meters per second. And then we have the radius of 0.50 meters, and we got a lot of info here. Alright, so now that I've kind of written that in a very nice sloppy manner as always, let's see what we get. So dividing this, we are going to get that and do that. So what I'm going to get from all of my labor here is I'm going to get that the magnitude of the force of tension at the top is approximately 94 newtons. Alright, so being in 94 newtons, let's have a look at what's going on now. Alright, sorry, now that we got the 94 newtons for point A, let's move to point B. So for point B, we're going to have this force of tension still directed towards the center. So I have this Ft, and this time gravity here is going to be directed down. Now this may introduce a bit of an issue. Some of you might be like, what do I do now? Alright, Ft is directed towards the center of the circle. Fg, it's in the same plane as the circle, but it's not pointing towards the center, and it's not pointing away from the center. It's acting directly perpendicular to these two vectors. So here's the thing. Fg is actually not going to contribute to Fc. It's not pointing towards the center, nor is it pointing away. So this does not contribute. So what that means for us is, for this part here, the centripetal force is equal to the force of tension at this point. So to get the force of tension, we're just doing mv squared over r. So we have that 0.82 kilos, 7.9 meters per second squared, meters per second. All of that is going to get squared. Sorry for the whatever you want to call that, my bad writing. We'll divide that by 0.50. So what we're going to get here is we're going to get about 102 newtons. Now I have two significant digits everywhere. So I should probably write this as 1.0 times 10 squared newtons to respect sig digs. But yeah, if one of your vectors is acting tangent to the path, it will not contribute to the centripetal motion. So FG is not contributing to the centripetal force at this point, and only at this point, and the point opposite to that. Everywhere else, the force of gravity is going to have some contributions. So last thing, at the very bottom of the circle, tension is still going to be directed towards the center. But this time, the force of gravity is going to be directed away from the center. So we have to watch for that this time. As always, our equation is still going to be similar. The centripetal force is going to be the force of tension plus the force of gravity, or the force of tension is going to be the centripetal force minus the force due to gravity. This is where we got to be a little bit careful. This time, the force of gravity is pointing away from the center of the circle. So in this context here, G is going to be negative 9.81. So we have to be really careful with that one. Because otherwise, if we don't account for that, we're just going to get the same answer as we did in A. So I cannot stress enough, once again, be really mindful with direction and draw a free body diagram for everything. The free body diagram will save you a hell of a lot of frustration. So we're going to put that negative there, because again, away from the center. So we do that, we're going to get about 110 newtons. Or once again, to respect sig digs, we'll say it's about 1.1 times 10 squared newtons. But that's good. A has the smallest tension, C has the largest tension, B is kind of somewhere in the middle of it. So these are the types of problems you'll see in vertical circular motion. As I said, they're a little bit more involved and we have to be a little bit more careful. But if you take them slow, you do them methodically, you shouldn't run into any major issues. Don't rush anything. But again, I know you've heard me say this and you probably hate me for saying this all the time, but draw a free body diagram. There is no way to get around that. It is so critical. So do it.